In this video, we are going to do cluster analysis. And this type of analysis is really useful for market segmenting. And in this R script, this is a practice version where I prepare some blanks for you to replace with appropriate functions, objects, or parameters. And please try to reason through each step of the script to understand what it is doing. I will demonstrate how to use it. All right, the first step we need to do is to install all the package required to do cluster analysis. In particular, we need 4 packages: read Excel tidyverse cluster and open XLSX. Could you please just run the first code? And you will see the R is trying to install the first package. And please do the same for the next code. All right, the function install.package is trying to install the package, but we need to tell R to call the package to use. Okay, so right here we have some blanks. What do you think we should fill in right here? So we should call all the 4 packages we just installed. The first one is read XL. Then we just type read XL. Okay. The next one will be the tidyverse. We will do the same. And cluster already there. The last package we need to call to use is the OpenXLSX. All right, it's time for us to run the code. Let the library call the first package read XL. The next one, the next one, and the last one. Okay, so right now in our environment, we already have all the required package to perform cluster analysis. The first stage, we need to have the data and prepare the data a little bit. So the next step, we try to read the data file. In particular, the data file was provided in Excel version, and we try to use the function read Excel and store all the data in a variable called dent_max. Okay, so please run the code. And what do you see? You see that it's tried to open a new window for you to choose the data file. In particular, in my case, the data file in this desktop folder, and to choose it. Okay, right? And after you choose the data file, in the environment you see the data file name dent_max with 2,300 observation, which is very big, market-based, and with 19 variables, right? Now, the next code is view in the blank. What do you think? What did you name the data set? So basically, we already named the data set as dent_max, right? So we just replace the name. And then we run the code and we can see, we can view the data with 2,300 observation and 19 columns. Right, that is how we choose the data set. Now let's explore just a little bit. The first function we can use is names. Basically, this function will help us to show all the column names of the data set. Could you please let me know, or try yourself, what objects we should fill in here? What we want to see the names of the columns. So basically, we want to see the names of the columns of the object, then maps, right? Then just write the names. And please run the code. Right here, you will see all the column names: ID, time, time to, time total, by best. If you want to know the column name means, you need to check the data description, which is already provided to you. The next function we use is summary. So this function will help us to display some basic summary statistics like mean, max, etc. for each variable, right? And the same, right? We need to fill in the name of the variable that stored the data set, which is max. And please run the code. So right here, you will see the summary for each variable with the mean, median, mean, and max value, etc. Another function that can help you to explore the data in the first hand, that is structure. And right here, what do you think we should fill in this blank? So we need to see the structure of all the data set that we store in this variable, right? So we can key in the Denmark's data set and we can run it. All right, right here we can see the name of different columns, and for each column we can see the values. There's one thing we can see if we opened the data 5. So we can see we have the first column is ID. It's a little bit messy, so you might want to remove this column because, you know, in our studio we already have the ID itself, so we don't need this column, so we can remove it. And to remove it, we can remove the first column right here. So basically, in this blank, you can type 1, represent for the first column of the data set, and the minus sign is removing, okay? And please run the code. And to check if we already successfully remove the ID column or not, we can check the names of the columns of the new data set called DF. So basically right here, we should type DF. Look, now the first column is not ID, it is time. If we can trace back to the previous data set, the first column is ID, so we already remove the first column, right? And for the data set provided, because the company collected data using different scales. For some variables, they use survey item from 1 to 7 Likert scale. For some variables, they use yes, no. For some variables, they used basically just the number of the years, the number of the minutes, etc. So we need to standardize, you know, all the data to have a mean of 0 and standard deviation of 1 to make sure that the programming language will understand all the same way for the following analysis. So right here, you need to think of what data should be scaled. So basically, this is the data we need to scale, right? The DF, the data after we remove the ID column. So we just type DF. And we use the scale function to standardize all the data and store it in the new variable called dfz. And please run the code again. All right. And if you want to get the new standardized data, you can use the view function and put the new variable store the scale data dfz. And please run the code. Okay. The standardized data will look like this. Good. So we just finished the initial data exploration step. We can move on to the segmentation step. First, before we can run the clustering algorithm, we need to compute the pairwise distance between the rows of a dataset using Euclidean distance. Okay. In particular, we need to use this function. And if you have no idea what that function is about, we always can put question mark before the function and run the code. So immediately R will show you the formula how to use that function, right? So right here, you don't need to worry about the other parameters. Let's insert the key parameters for this function. So in the first place, the object we need to key in, that is the data set, right? Itself after we standardized. So the data set after we standardized, we call df set. So let's call it df set. And the method, of course, we are calculating ULID. So just type the name, but make sure that you type correctly as is mentioned in the documentations. You always can check documentations. You don't need to remember how you use the function. You always can check the documentations. And right here, you can type ULID. All right. And let's run it. Great. After you already have the Euclidean distance already, you can start to prepare the cluster dendrogram. Okay, and to do that, we need to perform the hierarchical clustering. We need to use the functions hclust. And if you have no idea what that function is about, you again can put the question mark in front of the function and see, or will tell you how you could use the function. All right, so right here, I create a new variable called hc.w, represent for hierarchical clustering using the Wadi linkage. Okay, so for this function, the first object we need to key in is the distance. And remember, we just computed the distance above. So we should put that variable here. All right. And the method, as I mentioned, we have several, linkage methods. But in this case, let's use the wordy linkage method. All right. If you are not sure how to type correctly, you need to check the documentations again. Right, let's run it. All right, we just performed the hierarchical clustering analysis. Now let's see how the dendrogram look like. We can use the plot function and we plot the clustering result we just computed above, which is this one. All right. And in the main, we will specify the name of the plot we would like it to be, and X label. What is the label for the XYZ? Remember, for the dendrogram. So on the XYZ, basically, we need to show all the data points and in particular customer, right? Right here, let's call it observation. All right. And on the dendrogram, what is the Y label? The Y label is about the height. This is about the differences, right? Between the clusters. Good. Now let's run the code. Okay. So right here, you will see the X label is observation, and you see the Y label is height. And the name of the plot is cluster dendrogram. You can see here, you can zoom in the plot, right? Okay. So you can imagine because we have like 2,300 observation, that's quite a lot of customer here. So we see a lot of black color here. So it's normal, okay? All right. Let's go back to the R script and run the next code. So after we have the cluster Dendrogram, remember I mentioned to you that to choose the optimal number of cluster, you need to use your domain knowledge. You need to use your experience as a marketing managers. There's some method that we can use as a starting point to decide the optimal number of cluster. For instance, the elbow method. Okay, and the code here will show you how to show the height from the clustering result and sort them in the decreasing order. This code will prepare a vector from 1 to 10. Let's run it. And then I try to extract the height, the dissimilarities between the cluster from the clustering result. So right here, I will type height. And remember, hc.w is the clustering result we just computed above. Okay, and let's run the code. We already have all the height from the clustering result. It's time for us to sort it from cluster 1 to cluster 10. Okay. And let's plot the elbow. So it's very similar how you plot the Dendrogram. Okay. You also need the plot title. Let's call it the elbow plot. And on the X label, on the X axis, the elbow plot, that is the number of cluster, right? And on the Y axis, we have the within cluster variance. Okay. So let's run the code. And let's color the line a little bit so to make it a little bit more beautiful. Okay. So right here, if you look at this plot, what do you think? Could you please read this line I prepared for you? After how many cluster and when you add more cluster isn't significantly improving the fit within the cluster, you can see this is the apple point, right? After 4 cluster, the variant is blend within the merging cluster is not that significant. So it's very parallel to the x-axis. Okay, so we can see the optimal number of cluster here in this case is 4, right? So you can type 4 here and 4 here, right? All right. Now, we already knew that the optimal number of cluster is 4. So let's try to show those 4 cluster on the Dendrogram. Okay, we can plot the Dendrogram again with 4 cluster. Let's run this code. Okay, remember the plot, a lot of black here. And this time we already know the number of the optimal number of cluster, which is 4. And we run it. See, now we can cut the cluster Dendrogram into 4 cluster, which is optimal. All right, so we just visually see how the cluster are assigned or how, many segments in the market, but we need some specific data from those cluster. That's why we need to move on to the next step. We need to assign each observation to a cluster. In particular, we can use the function cut tree. Okay, we can cut the clustering result into 4 cluster. right? And store it in the cluster variable. Good. Now, it's time for us to know what is the size of each cluster or of each segment, okay? We can use table cluster, okay, right here. So you can see we have 4 cluster. Cluster 1, 1,127 observation. Cluster 2, 506 observation. Cluster 3, 276 observation. Cluster 4, 391 observations. Okay. So it seems like the first cluster is quite huge. Now, to continue, we need to combine the cluster data with the original data using cby function, column combine, okay? So we can combine original data and cluster. So what do you think we should fill in here? So I already have cluster here. So basically this should be the original data, right? And what is the original data? Do you still remember what variable store our original data? Okay. Is it DFZ? No, this is the standardized data. We don't need it because we need to interpret the data. We need the more original one. Is it Denmark's or is it DF? Denmark's have 19 variable, DF have 18 variable. Remember, we want DF because we don't want the messy ID columns, okay? So let's tell the program that let's combine DF and cluster data together and store it in a new variable called df final. Could you please run the code? Great. And then let's view the df final. Okay, you can scroll to the very right. And at the end of this data frame, you can see the last column is cluster with value 1, 2, 3, 4. What does it mean? It means that for each observation here, for each customer here, they will belong to one cluster. For instance, customer 1 right here, they belong to cluster 1, right? Customer 12, let's see. They also belong to cluster 1. Customer 13, they belong to cluster 4, right? Great. So we already finishing the clustering analysis. But as I mentioned to you a few times, running the code could be manageable. Learning the software is manageable, but to describe the cluster, to illustrate the picture of the customer is quite challenging. And to do this description step, we need to know some characteristic from the cluster data. First of all, we need to calculate the segment size. And to calculate the segment size, we need to take the number of the observation from each cluster and divide it by the total number of rows. And the total number of rows is, we know that's 2,300. You can put it here, 2,300, or you can do it another way. You can tell the program to take the total number of rows of your final data set, right? Your final data set is df final. All right, let's run the code. Great. Now you need to take that number times 100, so you will get the percentage and store that data in the percentage variable. Right. Now let's show the segment size in percentage. Do you think what we should put it here in this blank? Remember, we just store the percentage values in the percentage variable. So basically we need to print the percentage. variable, right? Look, we have four variable, 1, 2, 3, 4, and cluster 1 account for 49% of the market, cluster 2, 22%, cluster 3, 12%, cluster 4, 17%. All right here, you will use this function to summarize the mean of each column in the final data set by cluster. Okay, so let's run the code. And we can see the mean for each cluster. Right here, we store the mean of each cluster for each column in the object called segments. So let's run the next code and we will see. Okay, right here we have several columns. So the first column is show us which cluster, okay, that means belongs to. All right, right here, the next column is the time mean. If you check the data description, you will know this column is about the average time that the customer spent at the company booths, right? So in cluster 1, the average time that customers spend is around 12 minutes. For customer from cluster 2, they probably spend 36 minutes. For customer from cluster 3, customer will spend 45 minutes. And customer from cluster 4, customer will spend around 6 minutes. All right. To make it, a little bit easier for our additional analysis, we can store the result in an Excel file. In particular, we can use the function dry XLSX. Okay, right here, what do you think we should put here? We should put the variable segments, right? All right, great. Now we run the last code. Okay, and now you already have the new Excel file called segments.xlsx, okay? You can go to your working directory to open the Excel file. You just save, or you can check the file tab here and you will see, okay? Let me check what is my current working directory. So let's see. Okay, my current working directory is my download folder. And if I go to the download folder, and I can see the news file is the segments Excel file. And yeah, please open this Excel file. All right, so now you have the Excel file. I think it's much better that you can reduce the number of decimal places. Okay, it's look very nice now. So right now you already have all the means for each variable by cluster. Okay, cluster 1, cluster 2, cluster 3, and cluster 4. Your job doesn't end here. You need to interpret what does each mean value here to you. And that is the end of this video. So in this video, you already know how to run cluster analysis. You know how to draw the dendrogram. You know how to choose optimal number of cluster. And you also know how to describe the characteristic of each cluster or each segment. In this video, I will show you how to use the choice analysis or Logistic regression analysis to determine the impact of different marketing factors such as price, promotions, and so on the consumer choices. For instance, whether the customer joined a company or not. And this type of analysis will use the past behavioral data. And please remember, the outcome variables only have two choices or two level, yes or no, or 0 or 1. Okay. So in this analysis, we will use the dataset TKL. And before we begin, could you please load two relevant packages? The first one is the OpenXLSX to save the output to the Excel file, and the other one is ggplot2 and for plotting purposes. All right, so let's run the first codes. Cool. Next, on this slide, could you please run this one? And when we run this one, we will have a new window. Basically, the program asking us which dataset we want to use for this type of analysis. So we need to choose the relevant datasets. In particular, this is, in this case, that is the acquisition dataset. Because I'm going to try to run the acquisition choice model. All right, so if you see in the environment, we already successfully loaded the dataset with 2000 observation with 8 variables, right? The next one, what do you think we should view in these plans? So we just save the dataset in the object TKL-A, right? So we just mention again the object TKL-A, right? And if you run the code, you will see the data structure on the screen right now. In the first column, we have the variable acquire. That is the outcome variable. We have two levels, 0 and 1. 0 means the customer was not acquired. 1, the customer was acquired. And we have several predictors such as price, quantity, delivery time, sales support, industry, firm size, buying center. If you would like to know what are they about, you should read the case description and the variable descriptions. All right. Now we can do some initial exploration. We can check the column names of the data set, so we can use the names function with the object TKL-A, right? So right here, we can see all the names of the columns. We can use the summary function to check some basic statistic of each columns. And we keep repeating the name of the object that we saved the data to, right? So right here, you can see for each column, we will see some basic stats. Or we can use the structure function to explore the structure of the data set, the column types, the number of rows. Okay, TKLs, the A's again, right? So for instance, we can see 2000 observations, 8 variables, and we see the type of the column that is integer, right? And we see the first few values of each columns. All right, so there's one step is quite important. That is converting the scientific number to regular number format. What is that? Basically, in the Logistic regression outputs, most of the time you will see a few scientific notations. Okay, for instance, like this one, 2e minus 0.5. What does it mean? So if we do this step, we can convert the scientific number like this one to a regular number format. And let's run the code. Okay, and yeah, we already converted from 2e minus 0.5 to 0.00002. You will see this step is important later on when you analyze the output of logistic regression. Now, it's time to run the logistic regression. And to run logistic regression or choice model, we should use the GOM function. If you want to learn more about this function, you can ask for help. and you can read the relevant documentations. Okay, so basically to use this function, we should have the formula of the output of the outcome to the sign and all the predictors in the data set, or the relevant predictor that you want to insert into the algorithms. Okay, so what do you think we should fill in the plans right here? Okay, basically we should specify the predictors we want to put into the algorithm. Okay, you can see these are the predictors. So the first one is price, right? The second one is quarantine. The next one is delivery time. The next one is sales support. And the next one is industry. The next one is firm size. And the last one is buying center. All right. And remember, the outcome is binary. So we need to choose a suitable family for this kind of regression. GOM is used for several general line linear models. So we can check what could be the family for this type of function. So the one we would like to use is the binomial here, the link equal to logic. So we should specify it should be binomial, right? I think we can run the code already. Good. Now, we restore the output of GOM function to the fit object already. We can summarize this object to see the output. All right, so we have the output right here. Before we begin to interpret the result, let me show you another way to write the code. If we use all the predictors or independent variables. Okay, so in R, if we say the outcome, the tilde sign, and dot, basically we want to regress all the predictors on the acquired outcome. Okay, let's run it. And we have exactly the same outcome if we, specify specifically for each predictor. Right. Now, it's time to interpret the result, okay? So I give you some hints right here. It's good to read it. So you have 4 types of estimate. The first column right here, you have the coefficients. A positive coefficient means the predictor increased the likelihood of the outcome. In this case, that is the acquired. A negative coefficient means the predictor decreased the likelihood of the outcome. And larger absolute values of each coefficient indicates a stronger effect, a stronger weight on the outcome. A second column in the output, that is the standard error. The standard error measures the variability of the coefficient estimate, and smaller values indicate more precise estimate. The next columns, you have the Z value. Z value will be calculated as the ratio between the coefficients and the standard error of these first 2 columns. And higher absolute values of these Z values suggest stronger evidence against the null hypothesis. What is the null hypothesis in a regression analysis? The null hypothesis assumes that there is no relationship between the predictor or independent variables and the outcome-dependent variables. So in other words, it's assumed that the coefficient of a predictor variable is 0, meaning it has no effect. And a higher absolute value of Z suggests stronger evidence against the null hypothesis. which means that there will be a relationship between predictor and the outcome variable. And the last column, you have the p-value right here. So you have different significant levels, okay? So it depends on the number of the asterisks. So generally, if p-value is smaller than 0.05, the predictor is considered statistically significant. And lower p-value indicates stronger evidence that predictor has an impact on the outcome. Okay, so I just give you some hints. Now, could you please analyze the result of the logistic regression? Okay, for the price, okay, so what you see, this variable is significant. So price has an impact on the acquired outcome, in particular negative impact, which means with lower price, the customer more likely to acquire the product and service of the company. The next significant variable is quarantine. And with this positive relationship, it means that if the quarantine period of the company is longer, the customer may consider to acquire the product and services. All right, the next significant predictor is sales support. Similarly, if the sales support from the companies is better, higher, then probably the likelihood for customer to acquire the company offering is higher. All right, let's jump to the firm size predictors. We also have positive relationship, which means that for those customer as a business customer, the firm size of the customer bigger, the more likely they will consider the company product and service. All right. There is one interesting variable called industry. All right, so what do you think about this variable, how we interpret the result? If you read the data description, you will see that industry is a categorical variable with 3 levels. 1 stands for construction sector, 2 stand for industrial sector, and 3 stand for the OEM sector. Then how we interpret this number is quite challenged, right? And again, how you interpret the coefficient, the weight, if you put the absolute sign for all these coefficients, you will see the weight from the industry variable is the biggest one. So this is the strongest predictor. All right. So to interpret the industry variable or predictor more appropriately, we have something to do further. First, let's explore the industry variable. Okay. So let's use the table function to tabulate, to count the observation for each sector, each level of industry variable. We can type here industry, right? So we can see that we have around 650 observations for construction customer. We have around 1,000 observations for customer being in industrial sector and around 350 from customer being in OEM sector. All right. Now, with the original industry, it's quite challenging to interpret the meaning. We can't transfer each level of industry variable to a new binary variable, and we can use those new variable in regression analysis. Okay, so we can use the function if else. Again, if you have no idea about this function, you can use some help here. All right, and read the usage of the function. Right now, let's create a new binary variable called construction. Okay, so this function will look up all the value in the industry column, and if the value is 1, so it will return the true value 1 to the column called construction, right? If not, the column construction will have the value of 0. Next, we will create a new column called industrial, right? A new variable called industrial. Basically, this variable will look up all the value from the industry variable, and if any value is 2, then the function will return the true value, which means 1 for industrial variable. And if the value is different than 2, this function will return 0 for industrial variable. And similarly, let's create a new variable called OEM. The function will look up all the value from the industry variable. If any value equal to 3, the function will return the true value for the OEM variable. And the value from industry column different than 3, it will return 0 otherwise. And after we have the new 3 binary variables, remember, we should run the analysis again to interpret better the meaning of the impact of the industry and the outcome. How to do that? We can combine the original data TKL-A with the 3 new variable we just created above. Okay, so let's fill in the name of the 3 new variable. The first one is construction sector, right? The second one is industrial. And the last one is the OEM. So let's see if we type this correctly. All right, we didn't run these 3 codes, right? We need to run it before we can combine. All right, now we can combine ready. Okay, now let's check the column names of the new data set that we call DF-A. All right, so we have all the column names here, including all the original data from acquired column to bind center, and also included the 3 new binary variable we just created, okay? Okay, if you want to view the new data, you can view DF-A. Right? See, we have the binary value for construction, binary value for industrial, and binary values for OEM. Now it's time to run the logistic regression with the new data set, okay? So that new data set is DFA, and we can use the dot represent for all the predictors in the data set. But look, in this data set, there's one variable seems not so useful for us to interpret. Remember, that is the original industry variable, so we can remove that column. We don't need it in this new route of running logistic regression. And to specify it, we don't want that variable. We can specify the position of this variable, which is 1, 2, 3, 4, 5, and 6. So basically, we should remove the 6th column in the new data set. So we can minus the 6. And we run it. Here we are. So we have the good result, right? Without the original industry variable, but we see the result for construction sector and the result for industrial sector. All right. Now, another challenge, how to interpret the coefficient for the construction variable and the coefficient for industrial variable. Okay, I also prepare some notes right here. Could you please read and try to interpret the result with me? So the industry variable is categorical. We already created 3 new dummy variable for each category, right? And the elastic regression, I mean the new one, we use one category as a preference, the baseline group. In particular, in this example, they use OEM as a baseline group. The NA here doesn't mean that OEM does not have an impact on the outcome. Okay, it just means that OEM acts as a preference point. And the coefficient of the dummy variable show the effect of each industry type compared to the preference category. So this variable implies the impact of the customer being in construction industry compared to customer being in preference category, which is OEM. So a positive coefficient means that the industry type increase the likelihood of the outcome relative to the preference category. So it means that the likelihood of the customer being in construction industry to acquire the product and service of the TKL company is much higher than the likelihood of customer being OEM sector to acquire the product and service. And likewise, we also have positive number between industrial and OEM. It means that the likelihood of customer being industrial sector will buy the product and service from TKL is higher than the likelihood of the customer in OEM to buy the product and service from TKL. And these two effects are statistically significant. All right. So some of you might ask, what happens if we remove the OEM column because it's just a preference point? So we can do that. We can check the position of the OEM column, which is 7, 8, 9, 10, 11. So the position is 11 in the data set. So we can regress all the predictors on the outcome. We can specify that here. And we should remove the column that we don't want, including the original industry and the OEM column, all right? So the industry column is 1, 2, 3, 4, 5, 6. 6. Position is 6. So we specify 6. And the OEM column is 11. All right. Then we can run it. So we get exactly the same result, okay? Just without the OEM line. So the elastic regression will consider the last level of the industry variable as a preference point, which is OEM in this case, okay? So in the data set, OEM stay in the last position, okay, of the data set. So this one will be considered at the preference point for construction and industrial. Now, some of you might have asked, what happens if we consider another level as a preference point? It's totally okay. And we can try it now, okay? So let's run the elastic regression again with industrial as a preference point. How to do that? We can move OEM forward and make the industrial stay in the last position of the data set. So let's run it again so we can regress all the predictors on the outcome acquired here. We specify the dot. And at this time, we should specify the order of all the column. All right, so basically we need all the column with except the industry, and we change the position of industrial and OEM. So acquire 1, price 2, quantity 3, delivery time 4, sales support 5. We don't need industry, so we don't need 6 here. We need firm size 7. We need by center 8. We need construction 90. All right, now we need to change the position of industrial and OEM here. So we should put 11 and 10, right? And we can run. Okay, here we are. Okay, so we have slightly different result, but let's interpret it. Okay, so what does it mean when industrial as a reference point? So compare between the construction versus the industrial, the likelihood of the customer being in construction that acquire the product and service from TKL company will be higher compared to the likelihood of the customer being in industrial sector buying product and service from TKL. All right, now how we interpret this number. Okay, so this number means that the likelihood of the customer being OEM buying product and service from TKL will be lower than the likelihood of the customer being in industrial sector buying TKL offerings. Okay, do you see something similar? So if you look at the previous result, 0.411. If we compare industrial to OEM, industrial higher than OEM. This time we see the number minus 0.44. OEM is lower than industrial. So the result is the same. There's no difference at all. It doesn't matter which one is the preference point. It's more matter how you interpret the result. Great. Now, let's do another extra step. So to confirm what we have discussed so far, and let's plot the predicted probability by industry category. So in this line, I will compute the predicted probability of the acquisition using the output from our logistic regressions. Okay. Right. Now let's plot it using ggplot package. And we use the information from the industry variable and from the predicted variable we just computed right here. And we specify the label on X and on Y, and that's it. Okay, so right here, what do you see? We see industry 1 construction right here, right? We have industry level 2, which is industrial sector, and the level 3 is OEM. And we can see that the probability that customer acquire product and service from TKL between 1 and 2, construction will be higher. Between 2 and 3, industrial will be higher. Between 1 and 3, construction will be higher than OEM. All right, so we are good. All the analysis are consistent, for the insight that we can gain from. So we already finished the main step, how to run the choice analysis or logistic regression. Now, the rest of them, just about reporting and presentation. We already have the output from logistic regression. We can extract the 4 type estimate: coefficient, standard error, z-value, and b-value. Basically, we just replay the order of each estimate column from the output to the blanks here. Okay, so coefficients from the first column of the output, the standard error, the second column of the output, the z-value, the third column of the output, and p-value, the last column. So how we know that? You see, coefficient, the first one, standard error, second column, z-value, third column, and b-value, the last column. Okay, don't forget to run the code. Okay, we already extracted those important estimates. Now let's store those estimates in a data frame. Okay, so basically we just mention the object we store the estimate. Okay, so the first one is coefficient. Good. The next one, standard error. The next one, Z value. And the last one is P value, right? Now, see, if we view the data frame we just created, it looks much more beautiful compared to the original output from the Logistic regression. Now, it's very neat, easier to understand and interpret. And the last step, don't forget to save this table to the Excel just for further analysis in the future. So what do you think we should fill in here? That should be the data frame object, right? Estimate. Okay, you can go to the File tab and see if you already got the estimate.xlsx file. All right, so I just demonstrate how to use the code on one dataset, acquisition dataset. Could you please try to replicate the analysis for expansion choice model? Exactly the same, but remember, try to use the correct dataset. Okay. In this video, I will show you how to use t-test and ANOVA for experimental design analysis. Okay, let's first load the required packages. So here are the packages we required for today's analysis. So let's run the code. And here we will try to disable any scientific notations that appear in our analysis, just for easier interpretation. All right, now let's open our data file. If you are successfully loaded the data file, you will see the number of the observations and the number of the variables or columns. Now let's check the column names of our dataset. So the first column is customer ID. The next one is products, discount, conversions, advertisement, image, innovativeness, broadness, and involve. Let's summarize some basics statistics of each variables. Okay, so we have a few variables, but let's focus on the three main independent variables in this analysis. The first one is the products. We have two levels, 0 and 1. Discount, we also have two levels, 0 and 1. And for the advertisements, we have three levels, 0, 1, and 2. Now let's view the data set itself. Good. Before doing t-test or ANOVA, we need to pre-process the data a little bit. Our data is only possible for t-test or ANOVA if the independent variable is categorical or factor with different levels. We can check if the columns advertisement, discount, and products are categorical or factor variable yet by using function is.factor. And we just call the name of the column we want to check. In this case, it should be the advertisement. And the computer say false. It means the data is not categorical yet. And let's do the same for other two columns, discount. And products. The computer also say false. It means all these three columns are numerical rather than categorical. And we can convert these variables to factor type or categorical type by using the function factor. Let's run the code. And let's check if we are already successful with the conversion. by using again the function is.factor again. Now, these three variables already are factor or categorical and ready for the analysis. We need to create a new data frame that combines the existing data, excluding all numerical values, and adding the three new variables we just created. Okay, so first we can add the three new variables we just created right here to here. So the first one is add, the second one is this, and the last one is plot. And we should exclude all the numerical variables for the three IVs. Okay, we can open the data set and check where they are. So the first one is the second column, the third column, and the fifth column. So basically we can specify here 2, 3, and 5. And let's run the code. Now we can check the new data frame we just created with three new factor or categorical variables. So that's good. Now let's start with the independent t-test. So in 1A, we will test whether there is significant difference in the brand image between two different types of products. And we use the site package. And if you want to check the documentation, just question mark, and you will see the documentation about this package. In particular, we will use this package to describe some statistics by groups. All right, so right here, I will try to specify the dataset name, which is ABC, right? And here we want to tell the program to group the data by products. So which should be product. And here we will compute the mean value of the dependent variable, which is image, and standard deviation of image. Right. So we see we have two groups, 0 and 1, and for each group, we will see the number of the observation, the mean score of the dependent variable, which is the brand image, and the standard deviation of the image. Now we are ready to run the t-test for image based on the product. So in the first blank, we need to specify the relationship between the DV and IV. DV here is image. And then the student sign, and the IV is product, and the dataset name is ABC. All right, so here's the result of t-test. So let's analyze the t-test result a little bit here. I put all the notes here for your preference. So first, you need to understand what is the null hypothesis, H0 in t-test. So H0 says there's no difference in the average score of product 0 and product 1. Basically, two products are the same for the brand image. And second, you also need to understand the alternative hypothesis, H1. H1 says there's a difference in the means between product 0 and product 1. Basically, two products are different in terms of brand image. And here we have the t-value. So t-value indicates the standardized difference between the means of the two groups. And the negative sign here shows that the mean of product 0 is lower than the mean of product 1. And we have the b-value. So generally, the b-value will tell us if the difference between two groups is significant or not. And right here, we have very small value, so we can reject the null hypothesis, meaning we are confident that there's a real difference between the two groups. All right. And we also have the 95 confident intervals. This shows the range where we believe the true difference in average lies. Since the entire range is negative, it confirms that the product 0 average score is lower than product 1's average score. And importantly, we see the value 0 is not within this range, meaning the difference between the two groups is not zero. And of course, we have the sample statistic. We have the group 0 mean 2.75 and group 1 mean 4.09. Another way is we can confirm the t-test result by buck plot. Let's run the ggplot function. And here we can see the mean score in terms of brand image is quite different. Compare group 0 and group 1 in terms of product. In 1B, we will test if there is significant difference in conversion between the products. So it means product still be the IV and conversion is the DV. So we will calculate the mean and standard deviation of conversion for each product group. Right here, we need to specify the dataset name, which is ABC, and we will group the data by the product, which is brought. We need to compute the mean value of the conversion for each group. And right here is the standard deviation of the conversion. And let's run the code. All right, again, we see two groups with different mean score in terms of conversion. And let's run the t-test for conversion based on the product. You should try to interpret the result by yourself if you look at this t-test result. In 1C, we will test if there is significant difference in image between this count. So this count will be the IV and image still be DV. Again, we can calculate the mean and standard deviation of the image for each discount. Right here, we only need to group the dataset by discount. So we see the number of observation. We see the mean in terms of image for each discount type and the standard deviation of the image. And of course, we can run the t-test for image based on the discount type. So right here, we should specify the independent variable, which is discount. So here's the p-value. P-value is 0.1044, which is not significant as 0.05 level. In 1D, we will test if there's significant difference in conversion between discounts. We can calculate the mean and standard deviation of conversion for each discount. So we just run it after we specify the dependent variable here in the model, which is the conversion. And we are ready to run a t-test between conversion and the discount. All right, good. Now I will show you one way to summarize the result. I will create a new variable called relationship, where I store the direction of each relationship. And the second column I call it p-value, where I extracted p-value from the 4 t-tests we just run above. And then we will view the data. Let's run the code. And you will see something like this one, right? The direction of the relationship and their p-values. So you can accept or reject the hypothesis based on these p-value. Great. Now let's move on to the ANOVA analysis. So among the 3 independent variable product, discount, and advertisements, we have 3 groups: no ad with 0 value, ad 1 with value 1, and ad 2 with value 2. In 2A, we will check the effect of different ads on the image. So the IV is advertisement and the DV is image. We will use one-way ANOVA because we only have one single independent variable in this case. And In this case, it is quite useful to answer for the research question, does the advertisement strategy influence the image rating or the brand image? Okay, so let's run the ANOVA. We will store the ANOVA result in a variable called ANOV image. And right here, we need to specify the relationship between dependent variable and independent variable. The independent variable right here is at, right? So right here, we see the significant result, good. We can claim that the advertisement strategy will influence the brand image. But how is the variability between the groups? Because we have three groups, right? We need to do some further extra steps to know this. And before that, let's discuss how we interpret this ANOVA table. So right here, you will see the ad, which is our treatment variable advertisements. You see residuals. Residuals are the parts of the data that can't be explained by the treatment variable advertisements. Right here, we have the degrees of freedom. This indicates the number of the levels of the IV. So the IV have three levels, -1 is 2, so we have degree of freedom is 2. And 119 residual degrees of freedom suggest there are 122 total observations. 122 come from 2 plus 119 plus 1 equal to 122, accounting for all groups and data points. Good. We have sum of square. Sum of square measure the total variation in the data, and the total variation in the data come from two sources, the treatment variable and the residuals. We have the mean square. Mean square is the average variation. It is calculated by dividing the sum of square by the degree of freedom. And we have the F value. The F value tells us how big the effect of the treatment variable, which is advertisements, is compared to the random chance. And F is calculated by the mean wear of the advertisement to the mean wear of the residual. And the higher F indicates a more significant effect is this. And of course, we have the p-value, which is significant here. So generally, the p-value in F-test show the probability of observing the F-value if the null hypothesis is true. What is null hypothesis? The null hypothesis here is if there was actually no real differences between the ads. And the p-value here is very small, so we can indicate that different ads lead to significantly different results in terms of brand image. Right. Next, let's compute the mean and standard deviation for image with different ads. So right here, we need to group the data by advertisements, and let's run it. Good. Remember, from the ANOVA table, we know that the result is significant, but we have no idea which group is different from which group. That's why we need to do an extra steps that called pairwise comparison. And for pairwise comparison, we have some methods to do it. Right here, I use the two-key method because the sample size for each group is quite similar to each other. And to do pairwise comparison using two-key method, I will specify the ANOVA model, which is ANOV image. Right here. Let's run the code. All right, so now we have the pairwise comparison table. We need to understand what does it mean. So the first column, that is the comparison, group 1 versus group 0, group 2 versus group 0, group 2 versus group 1. And we have the mean score difference between two groups in each pair. We have the lower bound, upper bounds represent the range within which we are 95% confident the true difference between the two groups. And we also have the b-value. If you see the 0 is not within the range of lower bound, upper bound, it means that the difference is statistically significant. Okay, so in this case, which pair is significantly different? We can see the last pair, 2 and 1 is significant, and 95% confident interval shows that the difference is positive. There's no 0 within the range. It means the mean score of group 2 is higher than the mean score of group 1. In 2B, we will check the potential interaction effect between ads and products on the image. So basically, we have two IV, advertisement and products. The DV is still the image. In this case, we need to use two-way ANOVA because we have two independent variables. And we can use this one to answer to the research question. For instance, does the impact of advertisement on the image rating change around different products? And for two-way ANOVA, most of the time people are interested in investigating the interaction effect of two independent variables. What is interaction effect? This effect occurs when the effect of one independent variable on the dependent variable change, depending on the level of another independent variable. Let's run the ANOVA model. Here, we need to specify all the IV. So the first IV, we have a advertisement. The second IV is product and their interaction effect. Let's run the two-way ANOVA models. Great. So in this result, we see the main effect of advertisement on the image is significant. The main effect of product on the image is significant, but the interaction effect is not. Next, let's compute the mean and standard deviation for image for different product with different ads. Let's run the code. So we see we have 6 pairs of product and advertisements. The number of observation, the mean score in terms of image, and the standard deviation. Another way around, we can check the result by plotting the interaction effect. Okay, so let's run the code. And right here, we will use ggplot in the x-axis. That is different group of advertisements. On the y-axis, that is the mean score in terms of brand image. And we can color the plot using the product. Great. So usually you should align the plot result and the ANOVA result. So right here you see the advertisements and the product can individually influence the image rating. So for instance, product 1 quite perform well in terms of image rating, right? And for the advertisements, advertisement type 2 perform the best on the image rating. However, their combination or interaction effect is not significant. Why? Why we can claim that? The first thing is the visual impression. You can see the shape of product 1 and product 0 at different level of advertisements is the same, or the patterns is quite parallel between two products. All right. Or we can say the advertisement type influence ratings consistently across both products at zero level at 1 and at 2. Right. Let's continue into C. We will check the effect of different advertisements on a new dependent variable conversion. Let's run the model. Right here, we need to specify the dependent variable, which is conversion. All right. And we can compute the mean and standard deviation for conversion with different ads as well. Great. Now let's use two-way ANOVA again. So in this two-way ANOVA, we will check the potential interaction effects between advertisement and products on conversion. We have two IV, ads and products, and the DV is conversion. So we can specify here the DV is conversion. To the sign, the first IV is add, the second IV is brought, and their interaction term add colon product. Great. So if we look at this ANOVA result, we see the main effect of advertisements on conversion is significant. The main effect of product on conversion is significant, and their interaction effect is also significant. Right? And of course, we can check their plotting result as well. So let's run the code. So in this time, the plot is quite different, right? If you compare the shape or the patterns between two products, they are almost likely converge or crossing each other. They are not parallel anymore if you look at the previous lot again. So this plot is different, and that is the signal where the interaction effect is significant. So as a marketing manager, you can say product 0 will benefit more from the change in advertisement type from 0 to 1 compared to product 1 from 0 to 1 level of advertisements. In other words, the impact of advertisement type on conversion rating depends on the product. And I also prepare some code for you to check other potential interaction effects. Try it on your own. In this video, we are going to discuss the conjoint analysis. So, conjoint analysis is a special type of regression analysis, right? Now, first, let's install a new package called Conjoint. And if you already installed it, you don't need to install it again. And please load the required package of them here. All right, as usual, we will have some initial data exploration. First, for today, we have two data sets. So if you look at on the screen right now, you will see the first data set, it is about the bundles. We have 9 bundles, and we collect the rating data from 20 respondents. All right, and that data set we call conjoint. And for the second data set, that is the attribute information. So we have 4 attributes: life expectancy with 3 levels. The second attribute is speed with 3 levels. The aesthetics with 2 levels, and the price attribute with 3 levels, right? Now, let's open the conjoint dataset. And second, let's open the attribute dataset, which is profile. Great. Please make sure that you reload two required dataset properly. Now we can check the column names of each dataset. So for the DF dataset, we have 9 bundles. Is correct. We have the first columns right here. It seems like unnecessary that we are going to remove very soon. And let's check the column names of the profile dataset. So for the profile dataset, we have 4 attributes. Okay, and again, the first column is not necessary. The next step, we can check some basic summary statistics. Okay, let's do it with the DF dataset first. So if we look at this summary, we can see the scale for each bundle is on 0 to 100 scale. So basically, the company already collected the rating data from the customer on a scale 0 to 100. Now let's summarize the profile dataset. So in the profile dataset, we have 4 bundles, right? Life expectancy, speed, aesthetics, and price. And we can have the final look at each dataset. Now let's view DF. So the DF will look like this one, right? We have 9 bundles. And the rating for each bundle from customer on a scale 0 to 100. Now we can view the profile dataset. So we have 4 attributes again. Great. And to be able to run the conjoint analysis, we need to clean the data. We need to pre-process the data a little bit. Okay. As in the initial step, when we explore the data, we know that in the DF dataset, we have the first column correspondence rating, which is the row order. And we already have it in R, so we don't need this column, right? So we just remove the first column by specifying -1, right? And we can check the column names of the DF dataset again. Now, this look neat. We have bundle 1, bundle 2, until bundle 9 columns. All right, so remember, on the screen right now, I show you the basics of conjoint analysis. So it is a special type of regression analysis. And for dependent variable, it is already the rating from the customer, so it is continuous. But for all the independent variables, we need categorical variables with factor levels. Okay, we need to input the levels of each categorical variable into the regression analysis. And in this case, the dependent variable is the bundle rating from the customer. And we have 4 attributes: life expectancy, speed, aesthetics, and price. We need the levels from each of these attributes. Having said that, we need to check if these attributes are already in categorical format or factor or not. So we can check using the function called is.factor. So let's run the code for the column life expectancy first. Right? And we see the computer answer false. It means the current nature of the column is not categorical. Okay, we can do the same for the second column, which is speed, right? And we can specify speed here and run the code. And again, the computer say false. The column is not categorical. Let's check the aesthetics. Also false. Now check the last attribute, which is price. Also false. So all of these attributes are not categorical. And then we need to transform the attributes into factor variables by using the function called as.factor. So again, right here, we only need to convert those columns into factors and save the result in new variables. Okay, so right here, I will convert the life expectancy column. Let's call it life expect, right? And save it in the new variables. Let's do the same for speed and save it in a new variable called speed. And let's do the same for aesthetic. And do the same for price as well. Right. So we just transform all the attributes to categorical or factor variables. Now we can confirm again if we are successful with the change or not by using again the is.factor function. Now the computer says true. So it means that the variable, the attributes, has been converted successfully. And let's do the same for speed. True. Aesthetics. True. Priced. True. Now we are safe with the control analysis. But before we run the control analysis, we need to create a new data set with these factor variables. So basically, we just create a new data frame and we store all these four variables we just created above. The first variable is life expectancy. The second variable is speed. The next variable is aesthetics. And the last variable is price. Great. And let's view the new data frame. This looks nice and neat, right? And one more thing I always suggest you to do is it's very important to make sure that the order of these new data sets follow the original order of the data. What is the reason for this? Because when a customer rate each bundle, they will read the characteristic of each bundle. Basically, they read all the attributes. They just don't evaluate each attribute separately. And we need to keep that original order for our data set, no matter what we are doing with the data. For instance, like cleaning, arranging the columns, but always try to make sure that we need to keep that original order on the attributes as how customers saw it in the survey. Great. And in this case, now the order is exactly the same as customers saw all of the attributes in the survey. All right, so again, we already have the bundle level data. We have the attribute level data. Now, another type of data that we need, like on the screen right now, you see, is the attribute level data. So basically, we want a column that store all the attribute levels, all the levels in one columns, like this one. Okay, like for instance, life expectancy had 3 levels. We stored those 3 levels, and next speed had 3 levels, and next aesthetics we have 2 levels, and price we have 3 levels. All of those will be stored in the same columns. How to do that? Basically, right here we need to create a new column, right? And could you please fill in the blank for the missing levels? So you can see the first 3 levels here belong to life expectancies, right? Now, what are missing levels? Basically, the missing levels belong to speed, right? So if you forget what are the levels of speed, you always can check back the profile data set. So for speed, you have 3 levels, 1.0, 1.2, and 1.5. So we can type it here. Great. Do you see any difference, any weird here? The color, right? If we type the number like this, the computer will understand the value we just key in are numbers, not characters. So we need the quotation, right? Great. Now, let's run this live code, okay? And right here, you see, this is the column at attribute level. And we need this column for further analysis. Great. So we just prepare the data, we just clean the data a little bit, and now we are ready to move on to the conjoint analysis for each respondent. So again, as I mentioned in the lecture, for control analysis, you can run the analysis for each single respondent. And at the same time, you also can run the analysis for all the respondents. Right. Now let's start with the control analysis for the first respondents. Right here, we need to use a new function called CA model. Please question mark the function. And please read the instruction right here. And make sure you read it and understand how to fill in the blanks right here, right? So to use this model, we need y and x. What is y? Y is the vector of preferences and should be like a single profile of preferences. What does it mean? Basically, right here, we need the rating from the first respondents, right? And that data come from DF dataset. And in particular, we need the first row of the DF dataset. We need the rating from the first customer for all 9 bundles, right? And right here, we can specify the first row of DF, right? Right. What is X? X basically the profiles of all the attributes. And we have that data set called profile. So let's run it. Great. So right here you see the result, the model result for the first respondents, right? In particular, for the first respondents, the first level of speed is quite important to them. And that could be different for the other respondents. Right. So right here, you only see the model result, the regression model result for the first respondents. But just in case you want to see the utility score for all the attribute level for the first respondents, we need to use a new function called CA utilities. Okay, you can question mark the function one more time and make sure that you read the instructions right here. And to use this function, we need X, Y, and Z. What is Y? Y is the matrix of preferences. So basically, again, we need the rating data from the first customer. That is DF, first row, right? And of course, we need the profile of all the attributes stored in profile data. And what is that? Remember, we just created attribute level data, the column storing all the levels. And we call that column is attribute level, right? Great. So let's run the code, okay? The code not only give you the utility score, but also give you a lot of useful plots, okay? So right here, you see the utility score of the first attribute, which is life expectancy. Low, medium, high, right? And right here, you have the utility score for speed, the second attribute, 1.0, 1.2, 1.5. And right here, you have the utility score for the first respondent for the price attribute 8, 9, and 10. And we have the utility score for the attributes of aesthetics. with no imperfection and minor imperfections. Because for the first respondent, only the first level of the speed is significant at 0.1 level, so we can justify only the speed, right? What does it mean, the significant level right here? So for the first respondents, they really care about the speed of the product. And in particular, the speed 1.0 is more important than the other level of speed. That's it, right? All right. And now we can print all the utility for the first respondents, right? Right. So here you see all the utility score for all the attribute levels for the first respondents. Now, can you challenge yourself and replicate the code for the second respondents? Right here, we again use the function CA model, right? We want to build a regression model for the second respondent. And again, we need Y and X. Okay, so what is Y, everyone? You need to read the instruction, right? Y is vector preferences. In particular, right here, we need the second row of the DF dataset, the rating data from the second respondent. And we can specify here DF2, the second row. And of course, we need the profile of the attributes. Okay. Here's the regression result for the second respondent. And you see it's different compared to the result for the first respondent. So for the second respondent, there are 3 attribute levels are important to them. And again, we can see the plot of the utility score for the second respondents. All right, so we can use the function called CA utilities. And we need Y, X, and Z. Z again, if you have no idea what Z is, you can question mark the function and read the instruction, right? Z is the level, the attribute level data, and we call it the attribute level, right? So right here, we already print all the utility score for all the attribute levels for the second respondents. But if you cannot see the utility plot for the second respondent, it means sometimes the plot just hidden, underneath of the RStudio window. I will show you how to solve this problem, okay? So basically, you can minimize the RStudio window, right? And right here, you will see the utilities plot for the second respondents. Okay, so in particular, the first level of the life expectancy is important. The second respondent, they dislike the low life expectancy of the product, right? You see, this is negative value, and it is significant at 0.1 level, which is not that so strong effect. And for the second level of life expectancy, it is significant at 0.05 level, which is this one. It means that this person really like the medium life expectancy attribute of the product, right? And we also have the first level of the speed is significant at 0.1 level, which is this one. So it means this person also like the first level of the speed, which is the low speed, 1.0, right? All right, so let's come back to the R Studio, right? We just run the control analysis for every single respondents, but sometimes you want to run the control analysis for all respondents at one shot. In particular, in the case that you have a lot of data from respondents, like 500 people, like 1,000 respondents. And in that case, we need to use a package called Conjoint. And you can question mark the function of this package. So right here is the usage and all the instructions. We need Y, X, and Z again. Okay. So what do you think we will fill in this blank right here for Y? So this time we need all the data from the respondent, right? So that is the TF. We also need the attribute data, which is profile. And we also need the level data, which is attributes level. And let's run the model. And you see when we run the control analysis for all respondents, the effect is very strong, right? You can see it like here and right here. Now, we would like to create a table of the utility score for all attribute level for all respondents. Okay. And in this case, we will use a function called CA part utilities. We can question mark the function to read the instruction. So we need Y, X, and Z. Okay. Let's run the code. Right. Now you see that we just created a table with all the respondent in the first column, and we have all the utility score for each attribute level. Right. All right. So we just see that table, which is useful for sure, but we would like to know among the four attributes, which one is the most important one, right? And in this case, we use a new function called CA importance. We can question mark the functions and read the instructions. Okay. And in particular, we need Y and X. So what we should specify for Y? Y is all the data from respondent. I mean, the rating data, which is TF. And we need the profile of all the attributes, which is profile data set, right? And let's run the code. So here's the result. What do you think? Which is the most important attribute? If you don't remember the order of the column of the attribute dataset, you can click on this one and you see. So the largest percentage is 37.67, which represent for the speed attribute. So it means that the speed is the most important attribute for all respondents. Right, and I would like to show you how to plot the data we just figure out, and we can justify things like more visually, right? Let's first plot the attributes importance where we just calculated the percentage score here. Okay, so in this step, I will create a new data frame with two columns. The first column, I call it attributes, where I extract the column names of the profile dataset. The second column, I will get the percentage score from here, from in variables. Let's run the code. Now I will create a bar plot using ggplot2. Okay. So right here, I will get the data from importance df, right? I just created. And then I'd reorder the importance score. I choose the color for each bar is the sky blue color, right? And I want to add a point that show the data for each attribute Right here, I want to write the specific important values. For instance, like 35.91 for each important point. Right here, I want flipped the coordinate to make it more readable. And right here, I want to add the title for the plot, the labels for X and Y, right? And right here, I want to use a very minimal background. And last but not least, I want the title in the center of the plot, okay? Right, so let's run the code. So again, if you don't see the plot, the reason is sometimes the plot is underneath of the RStudio window. So here's the plot. So we have very beautiful plot, right? So you see, look at this plot, we see the speed is the most important attributes with 37.67% score. Right. Now, I want to show you another plot. Remember, we have the utility score for all the attribute level for all the respondents. That table is very useful for sure, but I would like to have very quick and powerful analysis of that data by creating a new heat map using ggplot2 package. And to create a heat map, we need to have some adjustment for the dataset. In particular, in heat map, only the long format data possible. What does it mean? So remember, we have the utility score, this one, in the previous analysis. Okay, so we have this table on the utility score. For all the respondents, this data is currently in the Y format. What is Y format? So the Y format means each respondent is a single row and each attribute level is a separate column, right? Each respondent is a row, each column is attribute levels. And we would like to convert this dataset to the long format where each row will represent a single pair of respondents and attributes, and the long format is useful for the heat maps. Now, let's run the code and convert the current utility score dataset to the long format. That's it. And when I convert from Y format to the long format, I would like to make sure that the utility score is a number and the attributes is factor. Now let's view the long one. So you see now each row is a pair of respondents and the attribute, for instance, right here, respondent 1 attribute low with the utility score, still respondent 1 with medium attribute level and the utility score, and so on. Right? And here we will create a heat map, very similar to the bar plot. Right here, we would like to color the utility score to create a heat map. I give you some explanation right here. Try to read all the instruction right here and play with the plot by yourself. So we have very beautiful plots, right? And I also provide you some interpretation right here. Let's have a quick look. Right, so on the x-axis, we have all the attribute levels. On the y-axis, we have the respondents from 1 to 20. And we color the utility score for each respondent for each attribute level. And if you see something very red, it means that attribute is really liked by the respondents. If you see something very blue or purple right here, it means that that attribute level is not liked by respondent that much, right? So as a marketing manager, you need to figure out what is your offerings-based strategy. So if you look at the patterns of the whole group, you will see this red column is quite preferred by the respondents, right? And the same for this column as well. And the same for this column as well. But the question is, what is the marketing insights? You need to think, analyze, and design the strategy for yourself. So for instance, right here, you see the price had 3 levels, but customer might prefer the reasonable price only, right? And right here, the life expectancy had 3 levels. The customer want to combine that reasonable price with medium term of the life expectancy. So try to think and analyze the strategy for yourself.